This video is about gravitation. I'll focus on how to find the weight or the acceleration due to gravity of an object or a body at a particular altitude or at a particular height on the Earth's surface. Now, let's say this is the Earth's surface, okay, and then there is a particular object, okay, at the Earth's surface right here. Now, okay, the force of attraction between the object at the Earth's surface and then the Earth is given by the radius of the Earth. Simply because, let's say there are two objects in space, the force of attraction between them, which is represented as F, is proportional to the product of their masses, and then it is inversely proportional to the square of the distance between them. The distance between them, let's say it is r, it is a center to center distance, and as a result, the force of attraction of an object on the Earth's surface is concentrated at the center of the Earth. So it is represented as the radius of the Earth. If I combine these two formula, the force of attraction of an object on the surface of the Earth will be given as mass of the Earth, mass of the object upon radius of the Earth squared. Okay, so there should be a square right here. Now, if I remove the proportionality sign, I will have an equal to sign, and then I will introduce a constant which is known as the gravitational constant. Okay, then I'll have the mass of the Earth, mass of that object, and then radius of the Earth squared. Okay, now let's say the object is not exactly at the surface of the Earth but at a particular height compared to the surface of the Earth. So let's say it is at a particular height h at the surface. Okay, now of course this is the radius of the Earth, which is represented as re. The force of attraction between these two objects, the Earth and then the object, is given as F, which is equals to g, mass of the Earth, mass of that object, upon radius of the Earth plus the particular height or the altitude, and then we'll have it squared. Notice that the force of attraction between the Earth and that object is the same, it has the same influence as the weight of the object. Notice that the object falls towards the center of the Earth, which is actually the definition of the weight of an object. But actually they both accelerate towards each other. The Earth moves towards the object, and then the object also moves towards the Earth, but the Earth accelerates slowly because it has a larger mass, but the object accelerates very very fast, and then it because it has a smaller mass. And that's actually according to Newton's first law of motion, law of inertia: more masses, less acceleration; less mass, more acceleration. So we look at it this way: the object tends to fall towards the Earth. Okay, so the force of attraction is given as the weight of the object, so we can make use of this formula for the weight of that object. Okay, so this is also given for the weight of the object at a particular altitude. So we can say that the weight of an object at a particular altitude is proportional, is inversely proportional to the square of the distance between the two objects. So it can be represented in this manner. Okay, that is if we just want to compare the weight of the object and the distance between the two objects, and for this we'll have something of this nature. Okay, and then the square of the distance between them. Now let's solve some practice problems. An object that weighs 2700 newton on the surface of the Earth and is raised to a height, that is altitude, of 2 Earth radii above the surface, what will it weigh up there? So the weight of the object at exactly the surface of the Earth, let's say Ws, is given as 2700 newton, and then the weight of the object at a particular altitude is what we just need to find. Now let's do something of this. Now this is the earth, and of course this is the radius of the earth. Okay, the object, this is the object, and then the object actually weighs 2700 newton, which is ws. Now notice that 2700 newton will be equal to the gravitational constant, mass of the earth, mass of the object upon radius of the earth squared. Okay, and then we'll also have weight at a particular altitude to be equal to g, mass of the earth, mass of the object upon radius of the earth plus the particular altitude squared. Okay, so for the altitude it will just be something of this nature, like the diagram I drew the other time. This is the height, and then this is the radius of the earth. So the distance between the two objects is the addition of the radius of the earth and then the height. Okay, so that's what we'll have right here. Now let's say this is equation 1, and let's say this is equation 2. So to find the weight of the object at that altitude, we need to divide equation 2 by equation 1, so that we can say weight at that altitude upon 2700 is equal to weight of the object is equal to all of this. Okay, so I'll have something of this nature: g, mass of the earth, mass of the object upon radius of the earth plus that height or the altitude squared, then divided by then weight at the surface, which is g, mass of the earth, mass of the object upon radius of the earth squared. Notice that this will cancel out because it is common for the numerator and the denominator, so they will both cancel out. As a result, I'll have something of this nature: 1 upon this and then 1 upon this. So I'll have 1 upon radius of the earth plus that height squared, then divided by, okay, 1 upon radius of the earth squared. So it's just like having 1 over y divided by 1 over x. That's something of that nature. If I have something of this nature, I'll have 1 over y multiplied by x over 1, which of course is actually x over y. That means I'm going to have it something of this nature. Eventually I'll have r squared, okay, upon radius of the earth plus h, then all squared. Okay, so I'll have weight at the altitude and then 2700. Okay, so that is it. Then let's say, what is the radius of the earth? Radius of the earth remains the radius of the earth, but notice that the height or the altitude is given as 2 earth radii. So h is given as 2 times radius of the earth. So if I substitute the value of h as 2 radius of the earth right here, that means 2 radius of the earth plus 1 radius of the earth, I'll have 3 radius of the earth all squared. Okay, that's why I have the bracket. So I will just need to expand the bracket. 3 squared, that's 9, and then radius of the earth squared. Be careful not to square 3 right here. You may just mistakenly write something of this nature. No, no, no. Okay, they will both be squared. So I'll have radius of the earth cancelled. As a result, then weight at that particular altitude upon, no, at the surface upon 2700 is equal to 1 over 9. So if I multiply both sides of this equation by 2700, I'll have weight at the particular altitude upon 2700 divided by 9. Of course, if you do this correctly, you should have 300 newton. So that is the weight of the object at that particular altitude. It's reduced. All right, let's solve some other problems. It will really help you. Imagine a planet having a mass twice that of the Earth and a radius equal to 1.414 times that of the Earth. Determine the acceleration due to gravity at its surface. Remember, 1.414 is actually root 2, so it will be easy for us to just make use of root 2. Now let's have, okay, we have a planet that has a mass. Let's say this is the planet, and then this is the radius of the planet. Okay, don't mind my diagram. Now the radius of that particular planet is root 2, that is 1.414 multiplied by the radius of the Earth, and then the mass of that same planet is given as 2 times mass of the Earth. So don't forget that the force of attraction, or the weight of an object at the surface of that planet, is given as G, mass of the Earth, mass of the object, not mass of the Earth this time around, but mass of that particular planet, the mass of the object, and then radius of the planet squared. Okay, I would like to substitute the values so that I'll have G, 2 mass of the Earth, mass of the object, since mass of the planet is 2 times mass of the Earth, and then radius of the planet is root 2 radius of the Earth. Then I just have to square all. So eventually I'll have 2G, mass of the Earth, mass of the object, upon 2 then radius of the Earth squared. So I can decide to cancel out 2 on both sides, which of course I'll have mass of the Earth, mass of the object upon radius of the Earth squared. Now the question says determine the acceleration due to gravity at the surface. Now obviously this formula right here is the weight of the object at the on the Earth surface, but actually it is given as the weight of the planet. Okay, that means it means that weight of the object at the planet is actually equal to the weight of the object at the on the Earth surface, because that's what we eventually have. But let's see it. Okay, let's say an object is on the Earth surface like this. Of course we will have this as the radius of the Earth, and then the weight at the Earth surface would be G, mass of the Earth, mass of the object, upon radius of the Earth squared. So this formula, let's say it is equation 2, and then this formula, let's say it's equation 1. They are equal. So but then we can say that weight of the planet upon weight of the Earth, that means I'm dividing equation 1 by equation 2, which is actually equal to mass of the object times acceleration due to gravity at the planet upon mass of the object, then acceleration due to gravity at the Earth surface is equal to, if I divide equation 1 by equation 2, then they are equal. I'll have 1. Okay, so the other side will be 1, that is I'm dividing GMEM upon RE squared by the same equation, so it will be 1. Then I can also divide the masses. So gravitation, acceleration due to gravity on the planet will be equal to acceleration due to gravity at the Earth surface, which is actually equal to 9.81 meter per second squared. So if you don't understand how I arrived at 1 right here, it is just like writing all of this formula, GMEM upon RE squared. Then I'll write that of equation 2, but they are the same, GMEM upon RE squared. So it will eventually cancel out to be 1. So I can multiply both sides of this equation right here. I can multiply both sides of that equation by the acceleration due to gravity at the Earth surface, which I wrote as GE. So I'll have something of this nature. Or you can say I cross multiplied. That is GP upon GE equal to 1 over 1. So if you cross multiply, then you have GP equal to GE, which is 9.81 meter per second squared. So there should be a square right here, because it's an acceleration. Now let's solve the next problem. A girl weighs 569.37 Newton on the Earth's surface. What would she weigh at a height above the Earth's surface of 1 Earth radius? What would her mass be? Okay, now the weight at the Earth's surface is given as 569.37 Newton. Okay, all right, and then we need to find our weight at a particular height of 1 Earth radius. Okay, that height as the height, which is h, is 1 times radius of the Earth. Okay, so that means the height is equal to radius of the Earth, and of course the weight at that particular height is what we are looking for. So let's say 569.37 is equal to g, mass of the Earth, mass of the object, upon radius of the Earth squared, and then weight at the particular height is equal to g, mass of the Earth, mass of the object, upon radius of the Earth plus the height. Notice that the height is 1 Earth radius, so I'll have another Earth radius right here, so that becomes 2 Earth radius. So instead of I'll just write it straight away as 2 Earth radius. So I'll have 2 radius of the Earth all squared. So eventually I'll have g, mass of the Earth, mass of the object, upon 4 radius of the Earth squared. So let's say this is equation 1 and then this is equation 2. So if I divide equation 1 by equation 2, I'll have weight of the object at a particular height upon 569.37 is equal to, if I divide equation 1 by equation 2, I'll have 1 over 4. That is, this will cancel out with this, and the radius of the Earth square will cancel out with radius of the Earth square. So of course, I'll have 1 at the denominator. So eventually, the weight at the particular height will be equal to 569.37 divided by 4. That's supposed to be 142.34. 142.34 Newton. So that is the weight of the object at a particular height, which is equal to 1 Earth radius. Now, what would our mass be? What would be our mass if the weight at that height is equal to 142.34 Newton? But notice that weight is equals to mass times acceleration due to gravity. So weight at a particular height is equal to mass times acceleration due to gravity at a particular height. That means we need to find what the acceleration due to gravity is at that particular height. Now to do that, I'll still make use of this equation right here. Okay, but I will not make use of this weight. Okay, so weight at that particular height, which is equal to mass multiplied by the acceleration due to gravity at the particular height upon the weight of the object at the Earth's surface, and that's mass of the object divided by the mass of the object times acceleration due to gravity at the Earth's surface, equal to 1 over 4. Notice that mass of the object will cancel the mass of the object, and then acceleration due to gravity at that height will be equal to acceleration due to gravity at the Earth's surface divided by 4. Okay, acceleration due to gravity at the Earth's surface is 9.81, so I'll have it divided by 4. So 9.81 divided by 4 is equal to 2.4525. 2.4525 meters per second square. You can see that the acceleration due to gravity is reduced at that height, and of course that means the weight, which is actually equal to 142.34, will be equal to the mass of the object multiplied by the acceleration due to gravity at that height, and of course the acceleration due to gravity at that height is 2.4525. So I can decide to divide through both sides by 2.4525, divide through both sides by 2.4525. So this will cancel out, this will cancel out. That means the mass of the object is equal to 1434 divided by 2.4525, which is equal to 58 kilogram. So 58 kilogram. So that is the mass of the girl at that particular height. Okay, so that's it about that. Let's solve another practice problem. Find the acceleration of gravity at an altitude of 1000 kilometer. Okay, the weight of the object at the earth's surface, which is actually equal to mass times acceleration due to gravity at the earth's surface. Of course, that is equal to g, mass of the earth, mass of the object, upon radius of the earth squared. And then at a particular altitude, I'll have mass times acceleration due to gravity at the particular altitude, which is equal to g, mass of the earth, mass of the object, upon radius of the earth plus the altitude. But in this case, we have it as 1000 kilometer. Okay, so I will just have it as h right here squared. If I did, let's say this is equation 1 and then this is equation 2. If I divide this equation 2 by equation 1, no, I would like to divide equation 1 by equation 2. I'll have, if I do that, that means the common things will be cancelled out. That is, mass of the object will cancel out, so that I'll have acceleration due to gravity at the earth's surface, at the particular altitude, upon acceleration due to gravity at the earth's surface, to be equal to, this will also cancel out, so to be equal to, I have this at the numerator to be equal to 1 over radius of the earth plus the height squared upon 1 over radius of the earth squared, which is equal to radius of the earth squared upon radius of the earth plus the height squared. So it is the same as having radius of the earth upon radius of the earth plus the height all squared, since square is common to both numerator and the denominator. So I can begin to substitute my values. I would like to use radius of the earth as 6570 kilometer. So if I solve in kilometer, I'll have 6570 kilometer upon 6570 kilometer plus 1000 kilometer all squared. Notice that if I make use of 6570 kilo means 10 raised to power 3, that's 3 zeros, upon 6570 kilo plus 1000 kilo. You understand, that's just like having 6570, then 3 zeros plus 1000 kilo, that's 3 zeros then another 3 zeros. Is the same thing as having this. All of the zeros will still have to cancel out, so I just want to avoid wasting time. All right, so if I had the denominator, I'll have 7570, then 3 zeros. If I divide the numerator by the denominator, I'll have 0.867. Then by squaring that, I'll have 0.7532. So eventually, acceleration due to gravity at the altitude over acceleration due to gravity at the surface will be equal to 0.7532. So acceleration due to gravity at the altitude will be equal to 0.7532 multiplied by 9.81, simply because I'll have to, okay, before I do that, I'll just have to cross multiply, and if I cross multiply, I'll have this. So this is actually equal to 7.7532 multiplied by 9.81. 9.81. So if I multiply that with 9.81, I'll have 7.39 meter per second squared as the acceleration due to gravity at that particular altitude. So it's as simple as that. Let's solve the last problem. An astronaut weighs 3,200 on a planet whose mass is same as that of the Earth but whose radius is half that of the Earth. So weight on that planet, which is equals to 3,200, is equal to g mass of the planet, but actually mass of the planet is equal to the mass of the Earth from the problem. So I'll have this, but the radius of the planet is half that of the radius of the Earth. So I'll write it in terms of the radius of the Earth. I'll write it in terms of the Earth. So it will be equal to g mass of the Earth, mass of the object, upon radius of the Earth squared, radius of the Earth squared upon 4. Alright, so it's just like having 4, then g mass of the Earth, mass of the object, upon radius of the Earth squared. So the astronaut weight on the Earth is what we actually want to look for. Now notice that weight at the Earth surface is given as g mass of the Earth, mass of the object, upon radius of the Earth squared. So let's say this is equation 1 and then this is equation 2. If I divide the equation 2 with the weight of by equation 1, I'll have weight on the Earth surface divided by 3,200, and then weight on the Earth surface, some things we just have to cancel out. Okay, but I have weight at the Earth surface as the numerator, and then nothing is remaining, so I will have 1. But for the weight of the planet, I have 4 remaining, so I'll still have it right here, which is still at the numerator. So as a result, weight on the Earth surface is equal to 3,200 divided by 4, and of course that is equal to 800 Newton. Okay, now that's just the weight of the astronaut. So we may decide to find the mass of the astronaut since it is at the Earth surface, you know, and then the weight of the Earth is given as 800 Newton. So that is, we just have to divide by the constant 9.81, which is g at the Earth surface, which is 9.81. So if I divide 800, or approximately 10 meter per second squared, if I divide 800 by 10, I'll have an approximate value of 80 kilogram as the mass of the astronaut. So that's it. That's how to find the weight or the acceleration due to gravity of an object at a particular altitude. All right, so share these videos with your friends. It will really help them, and make sure you subscribe to this channel. I'll produce more videos that will help you in your studies. Have a nice day. Thanks.